Okay, let's begin. So these were the examples we had from last time. We're gonna finish them up. So last time, the first one is an application of implicit differentiation where last time I actually learned how to differentiate something like that. What was the rule? Do you guys remember? What rule would help us with something like this? 3 to the y. How do you go about differentiating that? What was the rule? Yeah?
We had the derivative of a to the x equals a to the x ln a, but for this you'd have to multiply it by y prime.
But we also had a rule that covered that case, right? A to the u. Right? So that's u prime a to the u ln a. We proved that rule last time using logarithmic differentiation, log differentiation. So that was a topic from last time. So that actually shows us how to differentiate something like this. Now it's very important that you remember that your a is greater than 0 and it is a constant for this rule to apply. And that definitely applies here. This looks like an a to the u where your 3 is in the place of a and your y is in the place of u. So that being said, if I have 3 to the y plus x ln y equals 4, how do I go about differentiating this, finding y prime? This next step here. Yeah?
So you apply that rule to the 3 to the y power.
What do we get?
So it's going to be y prime times 3 to the y times ln of 3. And then you do the product rule for the next part.
Right, there are two functions multiplying here, so we need the product rule. How would it look?
It's going to be x times y prime over y. And then plus the ln of y, or 1 times the ln. And then it equals 0.
Now what was the next step?
You're going to isolate the y primes to one side and the ones that don't have a y prime
Okay.
to the other
How
side.
do we, what do we move now?
So subtract ln of y. And then you're going to
So that takes care of that guy. But these two guys that have y primes in them.
Can you multiply by a y first to get rid of the y in the denominator of one of the terms?
I mean, you could. So now what?
Factor out a y prime from the left side. So it's 3 to the y ln of 3 times y plus x equals. And then you divide by what's in the parentheses.
And that is our derivative via what we call implicit differentiation. And yeah, this rule came in handy for the first term. Implicit differentiation is, of course, an overall process that you will need to know for the test. What about B? What are we thinking here? Yeah, Anna?
First I did y equals ex squared, e to the x squared plus x to the x squared.
Let's see.
Okay, and then,
And then I logged both sides.
so you wanna apply log differentiation?
And then that would be y prime over y equals, and then I distributed the log.
Oh, but you can't do that. Right, that's not a rule. Right? So remember, if you have ln of a plus something, it is not the same as ln of a plus ln of b. In fact, what is this equal to? Ln of a plus ln of b.
ln of a times.
It's ln of a times b. So, yeah, you can't actually do that, it's not kosher. So. Log differentiation, and I'll show you a slight alternative later, but log differentiation is, I guess, the way you want to approach this, but you have to actually apply that differently, because we can't actually distribute a log across a sum. Ideas for how to get log differentiation to work? Yeah?
So for in terms of working with e, x to the square would be 2 times 2, like it would be x squared, like e to the u is u prime e to u, so
Right,
it
okay.
would be 2x e to the x squared.
Right?
Um,
What about the other part? The x to the x squared.
would be x squared x to the x squared ln of x.
What rule are you trying to apply?
I'm trying to find a rule.
Do you have ideas?
The rule is like 1 plus ln x, right? For x to the x.
We did a problem last time, yeah, where we tried to find the derivative of x to the x, and it was x to the x times 1 plus ln of x. Right. Now, that was an example, that's not something that I actually expect you to memorize, although, yes, technically you could do that here with the chain rule. So you could actually just stack, like if this x here, that's actually, even with the chain rule, that's gonna be weird. Yeah, so we don't really want to do that, but there was a way that we derived this. What did we actually do to figure that out? Yeah?
Can you somehow isolate it so it's like e plus x raised to the x squared, like to get rid of the, because they have the same exponent?
No, you can't do that. That's distributing powers across sums. So if you have a plus b to the n, it's not the same as a to the n plus b to the n. You can't jump between these two in general. Yeah?
We ln both sides and then we found the derivative of each term.
Right, that was the original idea, but that
Yeah.
doesn't work because you can't take the ln of a sum. Other ideas? But the fact that they're being added together is a problem for the log because I can't distribute the log and break it down simpler. ideas? What are we doing? Yeah?
Can you like subtract like the x to the x squared to like isolate the e and then read
Subtract it where?
to the other side to the left, so it'd be like
There's no other side.
y.
There's no other side. So here's the trick. It's a slight detour, but it's not. So one, you can realize that, well, we have a rule for e to the x squared, right? That's the derivative of e to the u is u prime e to the u. We don't have a rule for x to the x squared. So the thing is, I know how to deal with one of these guys, but I don't know how to deal with the other one. But we also know that the derivative of a sum is the sum of the derivatives. The first thing is to think of these two guys separately. So, of course, you had the right idea about somehow getting them isolated, but you can't really subtract from another side. That doesn't mean there's no other side to subtract from. But now you start to think of them just as separate things. I have a rule for this one, so I'm not worried about that one. This one, though, how do we figure that out? Well, what you would do is you would just, you go to the side, you figure that one out separately. So, this one here. Go to the side, you do your scratch work, and you just want to focus on how would I differentiate this guy? Okay? So now, how would I differentiate that guy? Like if that was just by itself, like what would I do? Like I have x to the x squared by itself. How do I differentiate it? Yeah?
Can you just take the log of that?
So you do log differentiation, right? So now we do, you can't just randomly take a log of something. So first thing you want to do is, now you can set up the equation, y equals x to the x squared. Because now, what was a problem before isn't a problem anymore, because I don't have a sum here. So I would log both sides. And that would allow me to simplify the right side. Now, this is a guy I know how to take the derivative of, because that's just product rule. Derivative of ln of y is y prime over y. Derivative of this is 2x ln x, plus you leave the x squared multiplied by derivative of the ln x. And so your y prime is just going to be y times this guy, 2x ln x plus x. And so that's going to be x to the x squared, 2x ln x plus x. And then what you do is now you go back and you plug this guy in here. So to find the derivative, this one is u prime e to the u, plus this guy, I went to the side, did it separately, x to the x squared, 2x ln x plus x. And that's your answer. So the trick here was simply just think of them one at a time. I have a rule for one of these, I don't have a rule for the other one, but I have a technique to figure it out. So I go to the side, figure out what that is with the technique, and come back, because the derivative of a sum is the sum of the derivatives. I can deal with them separately. Dealing with them together is an issue, because I can't get the log to distribute across the sum. Now, we'll look at a slight variation to this pretty soon, but for now, that's, based on what I told you last time, that's how you approach this. Now C, you do have a couple options for this one. It's the 7e to the 3x over x plus 1 to the 4th. Now you could go in directly, brute force, gung ho. This is America. Go big or go home. Do the chain rule with the quotient rule, with the product rule. And it's not going to be a fun time. But we learned log differentiation. So there are options now. Because I know that logs can turn powers into products, it can turn products into sums, it can turn divisions into subtractions. So if I could have an ln here, that would be super useful. So we can put one there. That's log differentiation. So what I'm going to do is set y equals this thing. And then I'm going to log both sides. So I create this equation that I'm going to log both sides of that equation. And now with the log in play, I am allowed to simplify this situation considerably. The power can come down in front, and I have log of blah over log of blah, which I know is log of blah minus log of blah. So this is basically going to simplify into ln of the top minus ln of the bottom, and there's a product in the top, so I can even split that into a sum. ln of x to the 7th plus ln of e to the 3x minus ln of x plus 1 to the 4th. I can simplify that even further. So the 7 can come down, 7 ln x, e's and ln cancel, that's just 3x, and the 4 can come down. Now, each of these individually are a lot simpler to differentiate than that guy. So at this point, I'm going to differentiate. Y prime over y is going to be equal to 1/3 times, it's going to be 7 over x plus 3 minus 4 over x plus 1. This means that my y prime is equal to the original function times 7 over x plus 3 minus 4 over x plus 1. And that is using log differentiation. So I told you how to use log differentiation already, but I guess I need to remind you of, or mention specifically differentiation. When is it useful? So certain situations, both base and denominator, base and power is a variable. Right? So if I wanted to differentiate, as an example, say x to the x cubed or anything like that, log differentiation is going to be useful. Just isolate the guy, set y equals that guy, blah, 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 do your log differentiation. Another situation is if you just have a complicated power that you don't want to have to deal with it as a power, right? You get a log in there, you can take the power, you can move it down and treat it as a product. Or you have a situation where the product, quotient, chain rules would be super annoying to apply. Right? Like in this situation. The thing is, the logs can turn products into sums, they can turn quotients into subtractions, right? And if there's a chain rule where there's like an outside power, the log can turn that power into a multiple. So logs can greatly simplify situations where to break it down by the product or the quotient rule or any of those stuff, it's going to be kind of really annoying. So it's very useful in that case. And of course, you have to be able to isolate it. You have to say y equals this thing that's complicated. You can find that. Sometimes you might have to find it separately. You break a problem into two pieces, do a log differentiation on one piece, do something else on the other piece. That's possible, but log differentiation is very useful in these situations. So it's something you might want to consider. So you see something like this show up on the test on Friday, you're not going to like, oh, let's do chain rule. Because one, you'll take forever. Two, it's complicated enough where even if you know what you're doing, chances are you're going to make a mistake. Why risk it? And three, there's a better way. Log differentiation. Log both sides, break the operations down, then take the derivative. It's nice that way. I want to mention a nice, which this is completely optional, but it's an alternative to log differentiation. So it applies the same principles, but it's just a different way of writing it down that some people might find nicer. So let me just mention that. So this is to use the fact that we know if I have something, and as long as it's valid to actually put it in a logarithm, I can write it as e to the ln of that something. So that was a rule that we had from lecture 2 when we spoke about logarithms, laws of logarithms. If the base and the base of the log, base of the exponential and the base of the log are the same, a raised to the log to the base a of something is just the thing. So you can in fact just use this rule. If I have something that I'd rather there be a logarithm in front of it to simplify it, I can just rewrite that thing as e to the ln of that thing. And I can do that right away. So, for example, if I ask you to differentiate x to the x, which we already did, but let's do it again, with this way, instead of going and saying set y equals this and log both sides and blah blah blah, I can actually rewrite this on the spot as e to the ln of x to the x. Right? Like I can do that. It's going to be valid. I mean, we're only considering this for positive x's anyway. There are considerable problems if you allow x to be negative here. And yeah, that allows me to actually rewrite the power as x ln x. And now it's just a u prime e to the u. So it's it's u prime times the original function. U prime is just the product rule. So you differentiate the x, leave the ln, plus you leave the x, differentiate the ln. So this is going to be ln x plus 1, and this is just the original x to the x. So that's your answer. Right? To look at the second example that kind of stumped us for a while, say x squared plus x to the x squared. So I saw something like that, and it never occurred to you to split them up and deal with them separately. The thing is, by using this rule here, you wouldn't have to split them up and deal with them separately. You can just actually rewrite right on the spot. So this, I would just take a couple steps to actually rewrite this guy. So instead of x to the x squared, rewrite it as e to the ln of x to the x squared. Right? I could do that on the spot. I can simplify this even a little more. So this is e to the, I can bring the x squared down, x squared ln x. And now I can use the same rule to kill both of them, u prime e to the u, because these are both e to the something. So u prime e to the u gives me 2x e to the x squared plus u prime e to the u, well that's a product rule. Differentiate the x squared, leave the ln x, plus leave the x squared, differentiate the ln x, times e to the x squared ln x. Now to simplify this, that's 2x ln x plus, x is cancelled, x. And this guy is just rewriting the original function. So that's the answer. So that's the alternative. It's really just a different way to write things down. So instead of having to split something up and go to the side, set y equals this, log both sides, and then come back and plug in the answer, you can kind of do it all on the spot, all in one place. And some people like it. So if you're into that, it's cool. You do it this way all the time. If this confuses you, then forget it, go back to the old way. It's completely swappable with log differentiation. Just remember, for log differentiation, you usually have to set y equals this and then log both sides and do that. This allows you to do it all in one spot. You don't need to go separate anything. Just right on the spot, rewrite it with an E and an L. So, yeah, that's just for some variety there. It's a variety that some people actually like using, as opposed to having to break things up all the time. So, now in the meantime, if we want to have a little fun with a topic. So our next topic is actually, the next official topic is linear approximation, which one, probably can't do that justice in 20 minutes. And two, I figured I'd show you something that's, in theory, quick and easy to actually teach and get around, where I can throw some bonus problems in the test on Friday and you'd actually have a good shot at getting them correct. So I figured a nice topic to kind of tie a lot of things we've been doing together, both derivatives as well as this kind of stuff, would be L'Hopital's rule. So let's talk about indeterminate forms and L'Hopital's rule. Did anyone ever hear of L'Hopital's rule before? So I'm going to keep it very basic. So L'Hopital's rule is a rule that allows us to take limits of certain kinds of complicated expressions. So let's talk about what's an indeterminate form. So these are limit forms. So it's very important that it's not just something that's standing on its own, it's something that arises out of you trying to take the limit of something. Right? Remember those guys from way back, limits? It's a limit form that is ambiguous because of competing ideas. So these are, for example, infinity raised to the 0 is an indeterminate form. So you're taking the limit of something to a power. You notice that the base is going off to infinity while the power is going to 0. You get the form infinity raised to the 0. Now that is indeterminate because there are two competing ideas here. On the one hand, if the base is going off to infinity, shouldn't it kind of go off to infinity? Whereas on the other hand, if the power is going off to 0, shouldn't it be 1? Right? So is it 1 or is it infinity or is it something else? This is kind of crazy. Very ambiguous. This is an indeterminate form. You can't really know ahead of time how it's going to turn out. You have to just get your hands there to get very specific. Another indeterminate form is 1 to the infinity. Again, because you raise something to an infinite power, you expect it to grow huge, but if you have something with a base 1, you expect it to be 1. So how are these guys actually going to be reconciled? That's kind of weird. Another one, infinity minus infinity. Which is some people you might think, doesn't that cancel out and give you 0? Turns out there are different sizes to infinity, so this is also very ambiguous. This infinity could be bigger than that one, or vice versa, or they could be off by a constant, like you don't really know. Very ambiguous. Another one is 0 times infinity. Ambiguous because 0 times anything should be 0, but then infinity times anything should be infinity, so kind of weird. Don't really know how that's going to pan out, right? Here's some other ones. Infinity divided by infinity. So no, that doesn't cancel out because again, infinities can be of different sizes. So This infinity can be infinitely bigger than that one, or this one can be infinitely bigger than that one, or they could be a constant factor of. You don't actually know. So infinity over infinity, also indeterminate, have no idea what that is without getting into the gory details. Another one, 0 over 0. So again, can't divide by 0, but these are limit forms. So I'm talking about a situation where you're taking the limit of some division, and both the top and the bottom are approaching 0. They'll never actually get there. But if you see like the top and bottom going to 0, what do? What is that? Division by 0, totally confusing, doesn't make any sense. Now, it turns out, so these are the 6 indeterminate forms. When it comes to limits and infinities, these are guys that we don't know. There are many others that we do know, right? So like, infinity times infinity, that's not ambiguous at all. That's infinity, right? You have a big number times a big number. That's only going to go one way. But 0 times infinity, not exactly sure. What L'Hopital's rule does is it helps us with these 2 indeterminate forms specifically. Right? Which means, now I'm going to tell you how L'Hopital's rule deals with this, but another idea that you have to be aware of is there are times when, if you're in one of these other 4 situations, you're going to want to rewrite things so that you are now in these situations. And one thing that comes in handy sometimes is kind of this idea. This idea will often help us rewrite this, as well as just other random algebra tricks that we have up our sleeves. But 6 indeterminate forms, L'Hopital's rule helps us out with 2 of them. Let me tell you specifically how L'Hopital's rule helps us. So, L'Hopital. So, it's named after a guy that didn't actually come up with the rule, but was a patron of the mathematician that came up with the rule, so they put his name on it. And I think his name means hospital in French. So I think that's literally hospital, which I used to have students that used to joke about that all the time. I was like, so how do we find this one? Take it to the hospital. Yeah, just whatever. It's just some useless trivia there. So, L'Hopital's rule. It helps us deal with these 2 indeterminate forms. How? So, lots of preamble here, but we don't care about it. Basically, it's going to say, that, oh, suppose your functions are differentiable, and there's continuity requirements and all that. Don't worry about it. What you want to know is, suppose we want to compute the limit as x approaches something of f of x over g of x. And this gives either infinity over infinity or 0 over 0. Right? And of course, with the infinity over infinity, it could be plus or minus here. But just that you have the top is going off to some infinite number, and the bottom is going off to some infinite number. Or the top is going off to 0, and the bottom is going off to 0. Right? Then, and of course, this is assuming we can find derivatives and all that. It turns out that the limit of this limit is equal to the limit when you take the derivatives and replace the function. And whenever these limits both exist, whenever this limit exists, it will actually always give you the same answer as that one. So that's basically L'Hopital's rule. If you're in one of these 2 situations, here's something you can try. You can differentiate the top and the bottom. It's not a quotient rule. You're actually literally differentiating the top and the bottom separately. Differentiate the top and the bottom and take the limit of that. And if you get to an answer, that's actually going to be the answer to the original limit in the first place. Let's do some examples.
Would the derivative of infinity be 0?
No,
If you were to
that
take derivative?
derivative of infinity doesn't make any sense. Infinity is not a number or a function.
Which still exists.
So that's not, yeah, it's not really something you can say. Now, it turns out that the first two, you should actually be able to say what the answer is by eyeballing them. Does anyone have a guess as to what A and B should be? Based on previously established ideas? At the limit as x approaches infinity of e to the x over x. What do you expect that answer to be? Yeah, what else?
Just infinity?
Why?
Cause like e to the x is greater than x.
Right, so we looked at some ideas before that if I have, say, a polynomial, an exponential is going to be much bigger than that, even, and the logarithm is going to be much smaller than that. And beyond that, you're going to have like an x factorial, which we're not going to talk about, and then something like x to the x. So exponentials get much bigger than polynomials when you're going off to infinity, which means the top is much bigger than the bottom, right? So e to the x is up here, and then x is way down here. So you have a very large numerator, very small denominator, it's going to go off to infinity. So you'd actually expect it to go off to infinity. By similar reasoning, you'd expect b to go off to 0, because the logarithm is going to be smaller than the exponential. So I have a very small numerator and a huge denominator by comparison. So this should tell you that, expect that to go up to 0. But let's actually apply a rule here to justify this, to kind of write it down maybe a little bit nicer, not necessarily any more correct, but sometimes it's not clear to see that right away. But what you can realize is, hey, as x is going off to infinity, e to the x also goes off to infinity, right? Because my e to the x looks like this. And of course, x is going off to infinity. So what you'll notice is that this approaches a limit form of infinity over infinity. The top is going to infinity and the bottom is going to infinity. This is infinity over infinity. This puts me in a situation where, hey, I can use L'Hopital's rule. That's specifically one of the situations where I can actually do this kind of maneuver. So what I'm going to do is exactly that. This should give me the same thing as, if I differentiate the top, derivative of e to the x is e to the x, over differentiate the bottom, derivative of the x is 1. So it turns out if both these limits exist, then this answer is going to be the same as that answer. And to indicate that I've used L'Hopital's rule, usually what I'll do is over the equal sign, I'll write like an L apostrophe H to indicate to the reader that I'm using L'Hopital's. Yeah, there's this one.
Is this the same thing as like top heavy, bottom heavy ideas?
No, top heavy, bottom heavy is what you mentioned to me before. Like, applying this idea is the top heavy, bottom heavy idea. But this is a different way to essentially get to the same thing.
Oh, okay.
But this will also help you in other situations too, which by the time you get through this, you'll see what we're talking about.
So, just to be clear, you didn't need the top heavy, bottom heavy idea in order to answer this, is what you're saying?
You could do it. That's actually the easier way to actually do it. Yeah, A and B, eyeball it. I know what those are. But showing you how L'Hopital's rule deals with this to show you that they'll get the same answer. That's just that, which is infinity, as expected. Similarly, if I had a limit as x approaches infinity of ln of x over x, then yes, both the top and bottom will approach infinity. Logarithm grows like this. It goes to infinity as x goes to infinity, and x goes to infinity as x goes to infinity. So this is another indeterminate form, infinity over infinity. L'Hopital's rule applies. So by L'Hopital's rule, I am going to differentiate the top over differentiate the bottom. So now, this limit, if it exists, will give me the same answer as the original limit. And that limit, what is that? Limit as 1 over x as x goes to infinity. It's 0, right? So, makes sense, I can actually get 0. Alright, so those two aren't so bad. You could use the top heavy, bottom heavy idea on those, but I just wanted to show you an easy example of us applying L'Hopital's rule so you kind of get the idea. Now let's move on to something a little bit more exciting. Okay, what is this approaching? What is the form here?
You're approaching 0.
Is it? What does the x get closer? Getting closer to?
0.
What is the ln x getting closer to?
Or 0.
Infinity?
Hmm?
Is it infinity?
Which infinity?
Positive.
No. What does log look like? What does y equals ln x look like? Yeah.
No, I was gonna say that.
What's the picture of? So ln of x looks like this. You guys need to remember that. Sure to go over all this stuff on Friday, all this stuff from before. So, given that you know that's the picture, what is ln x approach? Negative infinity. So this is a 0 times infinity indeterminate form. Now, first thing to realize, this is approaching 0 times infinity, that negative infinity, whatever. But it's still a 0 times infinity idea. Now, another thing that you should notice is that L'Hopital's rule doesn't actually help us here, because L'Hopital's rule does not help us with 0 times infinity. So, how can I actually figure out what this limit is going to be? Is it 0? Is it infinity? Is it something else? Here's one thing you can do. You can do this little algebra trick, which is a very common thing to do. In a situation like this, I'm going to rewrite this so that instead of a multiplication, it looks like a division, and I can do that using reciprocals. So I can take that x and move it to the bottom by writing it as 1 over x. And don't freak out, we're going to 0. Yes, but we're never going to get there. The limit doesn't care about being at 0. I don't have to worry about division by 0 because I have a limit in front. So I'm never going to get to 0. Just want to know, what is this approaching? So I can do the keep, change, flip idea, get the x in the denominator. Now, if I examine this thing again, this is the same as that by just laws of algebra. The top goes to negative infinity. The bottom, what happens to 1 over x as x approaches 0 from the right? Yeah?
0.
No?
Oh, wait, x approaches 0.
Yes, so 1 over x, what does the graph of that look like?
Like that.
Like this. Okay. As x approaches 0 from the right, what is that?
Infinity.
It's going to infinity. Okay. So by me doing this rewriting here, I get infinity over infinity. And hey, L'Hopital's can deal with that. So that's what I'm going to do. I'm going to differentiate the top, gives me 1 over x, over differentiate the bottom, which is minus 1 over x squared. I can simplify this, keep, change, flip. That's minus x. And now, what does minus x approach as my x approaches 0 from the right? Well, it approaches 0. So that limit is actually 0. Turns out the x is going to get close to 0 a lot faster than the ln of x is going to get close to infinity. So while this guy is growing very large, this guy starts killing it from very early on. So it actually gets closer to 0 overall. And very common trick that you can do here, when you have a product, you have like a 0 times infinity or something like that. The trick is usually to move one of those guys into the denominator to get like either a 0 over 0 or an infinity over infinity situation. I could have moved the ln of x here, but differentiating 1 over ln x is harder than differentiating 1 over x, so I decided to move the x. But yeah, try the other one. So first, figure out what is the form that you're looking at in the first place. Determine, can L'Hopital's deal with this? If not, try to rewrite it some way that L'Hopital's can deal with it. So we'll stop there for now. We'll see you guys tomorrow. Practice the other one. So what I might do for the test on Fridays, I'll like maybe throw a couple of these in the bonus section or something. So technically you're not responsible for this on the test. If you know it, it'll be really cool.